Welcome to the second video of the set theory series. In this video I will talk a bit about formal logic. I will not go very deep into details, but I think it's important anyway to cover a bit of the basics. Today we will first talk about the syntax of formal logic. That is, we will explain what a well-formed formula is and how it can be constructed. The second part will be about semantics, and it will be about what constitutes a valid formal proof. In set theory, we will use formulas to describe sets. For example, the following is a valid set. So the set of all x such that x is strictly larger than 2. Now, the formula x strictly larger than 2 describes the set. However, we cannot allow arbitrary formulas. The reason for this is illustrated by Berry's paradox. The paradox goes as follows. We define an integer x, and we define x as the least positive integer that cannot be defined in the English language with less than 1000 letters. So let x For example, the number 30 can be defined with 6 letters, the letters T, H, I, R, T, and Y. It is clear that only finitely many numbers can be written with less than 1000 letters. So, we can certainly talk about the minimal integer that cannot be defined in the English language with less than 1000 letters. However, the definition of x is exactly this. This is the definition of x. But we have just defined x with less than 1000 letters. But x cannot be defined with less than 1000 letters. So this is a paradox. It is called Berry's paradox. The problem here is with the word defined. The word defined cannot be given a formal meaning. And this striking paradox also showed that not every English sentence can be allowed to define a formula. So we need to specify exactly what a formula is and what exactly is allowed. This is a job of syntax. But before we'll talk about syntax, we'll first make a small remark. It is conventional in set theory to assume that everything we work with is a set. So any mathematical object that we speak of must be defined as a set. For example, the numbers 1, 2, 3, 1000 and for example pi must all be defined as sets. Of course, one can and should still think of numbers like we usually do, and their properties will always remain the same thing. It is only now that we have given a rigorous definition of what a number is. While before in mathematics, we just left the concept of number undefined. How exactly we will define a thing like a number, a function, a relation, as a set, is something which we will deal with later. Let us first describe the logical symbols that are allowed. Firstly, we will have a list of variables. Denote these variables by x1, x2, x3, and so on. Then we also have a list of constants. We will denote constants like c1, c2, c3, and so on. For example, the mathematical constant pi will be a certain constant. It is a set actually that cannot change, while variables can take on different meanings. For example, if we write for all x, then this x will be a variable. Now of course we will sometimes use other names for variables and constants, but we can always use these names if we really have to be formal. Now we'll work with the following predicates. The predicate equals, and of course the interpretation is that something equals something else, and the predicate is an element of. These are the allowable predicates. And then we have some connectives. We have the connective negation, it negates a formula. We have the connective and. We have the connective or. We have the connective implies, and we also have the biconditional. Now, the or in mathematics, if you don't know, is special. If we say in real life the sun shines or the sun doesn't shine, it means that only one of the two holds. But or in mathematics, it is allowed that both hold. Then we also have a few quantifiers. We have the universal quantifier and the existential quantifier. And then we of course can also work with brackets. These are all the allowed logical symbols. I will not give a rigorous definition for these symbols. They are concepts and I will leave them undefined. Rather, the axioms and the inference rules, we will see shortly, will give rules on how to manipulate these symbols. However, the logical symbols we have just defined have obvious interpretations. For example, the universal quantifier is used as for all statements, and the existential quantifier is used as there exists a certain set. But their intuitive interpretation is not part of the definition. In fact, mathematical logic leaves the meaning of these symbols undefined. It is up to the people to interpret it suitably. Obviously, a sentence like X is an element of A will always be interpreted as X being an element of a certain set A. However, we can also interpret it as X is a friend of A. This is perfectly allowed. However, the axioms and the theorems later will make no sense at all under this interpretation. This view is a formalist view by Hilbert. He interpreted mathematics as a collection of sentences of logical symbols, and some sentences follow from other sentences using basic rules. This is a very rewarding view because it liberates mathematics from having to interpret its statements in the real world. This interpretation can vary between several people, so although different people might interpret the statements differently, they will still see the same logical symbols and they will still agree on those. This is the preferred view to present and to write mathematics, and you will see it everywhere. However, it is not a way to actually do mathematics. Whenever we do mathematics, we always have some picture in mind, and this is the Platonistic view. For the Platonists, the mathematic entities like sets, groups, numbers do in fact exist somewhere, even if it is only in our minds. So the logical symbols and the sentences do have a meaning and describe some reality. We will now define the notion of a well-formed formula or a VFF. These are formulas that we will work with in mathematics. In particularly, we should be able to write any formula in mathematics as VFFs. Now, we will define a well-formed formula inductively. So, let's begin here. If A and B are constants or variables, then A equals B and A is an element of B are well-formed formulas. Again, note that everything is a set, so A element of B always makes sense, or should make sense. Now, assume that P and Q are well-formed formulas. Then we can construct the following. Not P, and we add brackets, is a well-formed formula. P and Q is a well-formed formula. P or Q is a well-formed formula. P implies Q is a well-formed formula, and P if and only if Q is a well-formed formula. Finally, if X is a variable, then we can form the formulas for all X P, and there exists an X P. These are all well-formed formulas. Now notice it might be strange that we don't really have a set in which X belongs. Indeed, our quantifiers run over the entire universe, not just on some elements of some set. Now, if we want to form a quantifier like for all X elements of A, P, this can be done. This is called a bound quantifier, and it is means for all X element of A and P. So this means this formula. So it is just an abbreviation. For example, we can form the following formula, and it will be a well-formed formula. For all X, Y equals Z, or there exists a Y element of X. This is a well-formed formula, like you can check. Now notice we have used Y 2 times here, and it means something differently. Here, the Y is the Y of a quantifier. It's a variable of a quantifier. Here, Y is a so-called free variable. So we have used Y in 2 different cases. While it is not forbidden to do these things, we will attempt not to do it anyway. Also, we'll sometimes be loose in using brackets. So, for example, we can write the previous as for all X, Y equals Z, or there exists a Y, and X. So we will eliminate brackets. This is allowed. Now, if we want to do it formally, then we can, of course, but this is much easier to read. Now, let X, Y, and Z be variables. We will look at the following formula. For all X equals Y, and there exists a Z element of Y. We see that some variables are used after quantifiers. So the variable X is used after quantifier, and the variable Z is used after quantifier 2. These will be called bound variables. The variable Y is not used in a quantifier at all. These are called free variables. Now a formula will usually be denoted by a Greek letter. For example, we will denote this as letter psi, and it is conventional to add the free variables after psi. So here this psi Y. So for example, if we see a formula phi x1 xn, then this means that this is a formula, and x1 to xn are its free variables. Now if c1 and cn are constant, then we can substitute in these constants in a formula to get phi c1 cn. For example, if we substitute pi in this example, then we get phi pi, and we get for all x equal to pi, and there exists a z element of pi, where pi is not a variable anymore but a constant. Now that we know how to form correct formulas, let us see how to prove things. In order to prove something, you need a list of axioms. An inference rule is a way to find new statements from old statements. So if you start from axiom and you succeed in obtaining a certain formula by only using axioms or inference rules, then this is a valid proof of the formula. The formula will then be called a theorem. Now if phi is a statement and you obtain a certain formula psi by only using phi, the axioms and the inference rules, then we denote this as phi and then this symbol psi, and we say that psi is inferred from phi. For example, consider the following statements. Phi, Socrates is a man. Now we should be able to derive from these two statements the statements that Socrates is mortal, and our inference rules will indeed allow us to do that. And then we will write that the axioms that we will consider will be given shortly. But now we will give the inference rules. The first three inference rules involve negation. Firstly, the inference rules that we can introduce negation. And it says that if P implies Q and P implies the negation of Q, then we can always infer that not P holds. So P and Q should here be interpreted as well-formed formulas. And this actually allows us to do proofs by contradiction. So this is the first inference rule. The second inference rule is the elimination of negation. So if not P is true, then we can always infer P implies Q, where Q is an arbitrary statement. So this means that from a false statement, we have considered that not P is Q, so P is a false statement. You can always infer anything you want. Now a system will be called inconsistent if there is a true statement such that its negation is always also true. Now from this inference rule, we can find that an inconsistent system, all formulas will in fact be true. This is why this inference rule is sometimes called the principle of explosion. Finally, we have the double negative elimination. And it says that from not P, we can infer P. So, if the food is not cold, then the food is in fact warm. And now we'll give some inference rules for conjunction. Conjunction means and. The first inference rule says that if both P and Q are true, then we can infer P and Q. The second inference rule allows us to eliminate a conjunction. And it says that if P and Q are true, then we can always infer P. And of course, we can always infer Q. These rules are very straightforward, and it exactly decodes what AND is supposed to mean. The next two inference rules will be of disjunction. Disjunction means or. And it says that from P we can always infer P or Q, where Q is an arbitrary formula, so no matter what. And of course from P we can always introduce Q and P, so the order doesn't matter. Then we can always eliminate disjunction as well, and the elimination says that from P or Q, from P implies R, and from Q implies R, we can always infer that R is true. So indeed, if P or Q is true, and if both P and Q imply R, then R must be true. Next we have some inference rules about conditionals, or implications. Now, we can always introduce an implication as follows. If we already have proven from a certain list of axioms sigma, and from a certain statement P, we have already inferred that Q holds, then from sigma alone, we can always infer that P implies Q holds. So this allows us to introduce implications. Now, to eliminate implications, it can be done as follows. From P, and from P implies Q, we can always infer that Q holds. This is sometimes called the modus ponens, and it is extremely important. Finally, we give the inference rules for biconditionals. These are all very straightforward. Now, to introduce a biconditional, it can be done as follows. From P implies Q, and from Q implies P, we can always infer P even only if Q. To eliminate biconditional, from P even only if Q, we can of course always infer that P implies Q, and also from P even only if Q, we can always infer that Q implies P. Now let us give two examples of proofs. For example, let us prove that the following is valid. Phi implies psi implies phi. So this means that if we have no axioms at all, so here is nothing, if we have no axioms at all, then the following formula is always true. So this is true without axioms. Now the proof is as follows. Clearly, from phi and from psi, we can always infer phi, because we know phi is true, so we can infer that phi is true. This is logical. Now we use the conditional introduction to introduce a conditional. And so we get from phi, we can always infer psi implies phi. Then we can use conditional introduction again, and we obtain the formula that we wanted to prove. As another example of a proof, let me prove de Morgan's law, or one of de Morgan's law. So it says that from not P and not Q, I can always infer not P or Q. Now from not P and not Q, I can of course always infer not P. And from not P, I can infer that P implies Q. Indeed, this was just the negation elimination. So, I can infer from not P and from P, I can infer that Q holds by the modus ponens, or the conditional elimination. But of course, from Q, I can also infer Q. So from the disjunction elimination formula, I have that from not P and P or Q, I can infer Q. So from not P and not Q and P or Q, I can infer Q because I can infer not P, but I can also infer not Q because I have not P and not Q. So I can infer a statement and its negation, so it means that P or Q must have been false. So this formula is proven. Here is a website where we can see some other proofs. Of course, all the proofs that we have done now can also be done trivially using truth tables. But if the statements involve quantifiers, then things are more difficult. So let me now present the inference rules for quantifiers. For the universal quantifier, or the for all quantifier, we have two inference rules. First, the elimination. So if C is any constant, then from for all x phi x, we can always infer phi C, where C is anything. And then the universal quantifier introduction. So if phi C is true for any constant, then we can infer for all x phi x. So phi C must be true for all constants. And then finally, the inference rules for existential quantifiers. So if phi C is true for some constant, then there exists an x phi x. This is true. This is the introduction of the existential quantifier. Then the elimination of the existential quantifier. If there exists x phi x is true, then we can always infer phi C, where C is a constant that was not used before. So it is a very new constant. Let us now give an example of a proof with a quantifier. We will prove the following. If there does not exist an x so that phi x is true, then we can infer that for all x, not phi x must be true. So phi x must be false for all x. So let C be an arbitrary constant. Now from phi C we can infer that there exists an x so that phi x is true. So from the following, there does not exist an x so that phi x is true, and from phi C we can infer this previous statement and its negation. So this means that not phi C must be true. So from this formula you can always infer not phi C. But C was arbitrary. So this means that we can infer this for all possible x. And this concludes the proof. Let us now introduce the axioms. In our study of set theory, we will always use the same axioms. And we can split those axioms in two parts. We have the logical axioms, and logical axioms, they deal with equality. And then we have the set theoretic axioms, and those involve the predicate is an element of. These set theoretic axioms we will introduce later in another video. Now we will focus on the logical axioms, the one that deal with the equality. The first axiom is for all x, x equals x must hold. The second axiom is a bit more difficult. Let phi x be any formula. Then we can form the formula psi y, and this is the same formula as phi, but we just replace all occurrences of x by y. For example, if we have for all z equals x, if this is our phi x, then psi y is for all z equals y. Now for the axiom says for all x and for all y, we have the following. If x equals y, then phi x must be equivalent with psi y. Notice this is actually not one axiom. Indeed, we have one axiom for every formula phi. So we call it an axiom scheme. It is an infinity of axioms, actually. Now, if we wanted to make it one axiom, we could, for example, put here a quantifier for all phi. But we cannot quantify over formulas. We can only quantify over variables. So this is not allowed. So we cannot see this as in fact one axiom, but as an infinity of axioms. Now the usual properties for equality, for example, this property, if x is y, then y is x, they can always be proven from these two axioms. So from this and from this axiom. But we shall not do this here. Now in what follows, we will never really prove any statements directly from the axioms and only using the inference rules. But it can certainly be done. But it's much too complicated and it's not very fun to do so. Now if you want to see a site where they actually do these things, then you should go to us.metamath.org. There they list many advanced theorems and they prove it from the axioms using inference rules. The site does in fact use some other axiom system and some other inference rules than we have introduced here, but the systems are in fact equivalent. This concludes this video. I hope you enjoyed it.